Is your coffee ready? I bet it is. Welcome back, and let's talk today about this paper called Simple Copy-Paste is a strong data augmentation method for instant segmentation. So this paper is a really nice one and actually super simple. There's not a single formula in the entire paper. So the basic idea here is to show that a really simple method named copy-paste is a really good way to have data augmented for instant segmentation problems. And why we need that? Well, you know that instant segmentation, which is, well, for those who are not familiar with, is basically a problem where you have an image with many objects in there. So let's say I have this person here, I have another person here that is 10 from the sun, and you basically want to have them segmented. So this is you do like you get the pixels that encompass this person and the pixels that encompass this person here, and also since it's instant segmentation, each object or each instance in the image is gonna get a different label. So let's say this is person number 1, this is person number 2. So this is instant segmentation. But what's the problem with that? What's the problem with instant segmentation? Why we need this? And the answer is data. Data set for instant segmentation is really hard to acquire. Just to give an example, 22 worker hours are enough to make 1000 instance masks for this data set called Quoc, one of the most famous in instant segmentation. So this is really low for deep learning standards, and you may imagine how much more you need, how many hours you need. So any method that can give you a boost without this crazy amount of work is really appreciated. So what does this paper proposes more specifically? If we see here their example, if you see their example here, basically what you want is to take two images with some objects that are already segmented, and you randomly put them together in one of the backgrounds. So you take background from image 1 or image 2, and then you take some objects from both, and then you just combine them. And that's basically it. You have some jittering on the size, so they call standard scale jittering and large scale jittering, basically to say that they perform both super big scale changes or standard ones, which are smaller, and they also perform the same scale or similar scales on the image. And when the scale is too big, they basically pad the rest of the image with gray. So you can see that this method is really simple. There's nothing special about it. They don't care about if the content matches, if it makes sense. They simply copy paste one thing on top of the other, and that's basically what happens. But you may be wondering, nobody tried that before? Well, in a sense, yes, but not exactly the way they propose. So there's a lot of data augmentation methods already on the market. You may be aware of the classic ones like random crop, color jittering, but they're not made for instant segmentation. They are made more for image classification. So they help instant segmentation, but it could be more than that. So there are another class of augmentation called mixing image augmentations, and there are basically three similar approaches to this one. The first one is the one called mix-up. So mix-up is a method where you take, again, two images, and you combine them. So let's say we have here a dog, really cute dog, and you have a cat. So just the head of this cat. And what you do, you just create an image and you put them together, but really like on top of each other. And again, it may seem really weird, but actually it works. So basically what you do, you blend them and use a value of blend. Let's say here you have 0.3 times cat plus 0.7 times dog. And so before, this image was, let's say, classified as dog, the left one, and the right as cat purely. Now you have this blended image, so the classification of this image is actually a vector. So basically you say that this image is 0.3 cat and 0.7 a dog. So this is mix up. The other method is called cut mix, and cut mix is again super simple. You have the two images that I draw here, and what you do is you just cut parts of one and paste on top of the other. So here you have, let's say we have the background as the dog, and you just take a portion of the cat, let's say top left, and you just paste it here. So you have this portion of the cat. And again, to make the label, you just do the same idea as before, that you just take this and say, okay, this is now cat, this part here is cat, and this part here is dog. So basically that's cut mix. And finally we have a third method, which is called mosaic, which was implemented in YOLO before, and yet another simple method where you take many images and you just concatenate them side by side in a mosaic style. So you just take those two images here and you make a new image where each one is one to the side of the other, and that's your new image. So it helped YOLO before, and it helps also in segmentation problems, and also super easy to implement. So as you can see, they are similar but not quite the same. They are not copy-paste pixel-wise of the objects. So you're always taking these bounding boxes and doing the things, while in this paper what you do is really take only the pixels that belong to the object and you paste one on top of the other, and you make a new image. So some technicalities about the method. They have this way of blending the images given by this little formula here, which is actually the only formula of the paper. You have a binary mask, which gives you the pixels that belong to the objects from one image. So you have image 1 times alpha plus image 2 times 1 minus alpha. And to smooth the edges, they have a Gaussian filter applied to those masks. And they have this large scale jittering and standard scale jittering that I talked before. The only thing about that you have to worry about is that it's simply a different scale in each case. So they do that for some experiments. So for the standard scale jittering, they just go from 0.8 to 125, while for the large scale jittering, they go from 0.1 to 2. So as you can see here, what it means is standard scale jittering goes more conservative, while large scale jittering you have really big scale changes. Now the really cool part of the paper, or my favorite part, is the experiment session, where they go really deep into showing empirically why this method works and in which situations. So I'm gonna skip the text here and going straight to the figures and tables because they are quite self-explanatory. So the first figure here is an example of different training configurations. So you have a same network that is trained in two situations. One, it's actually masked CNN that I'm talking about. One is randomly initialized and the other one is initialized with ImageNet. And as you can see, in both cases, curiously, you have the random initialization giving better results on the long run. They start with worse score, but they end up with a better average precision score. And also when they use, in this case, standard scale jittering and copy paste, it gives better results in both cases. So in both cases, the dot with square are the results with the copy paste method. And here in this figure, what they show is the same idea, but using standard and large-scale jittering, and now using random initialization. So basically showing the difference between using the standard and large-scale jittering. And as you can see, the green one, the large scale, actually gives way more improvements in average precision. And so it shows that this aggressive scale change actually helps on training masked CNN on COCO dataset. The other test they perform is trying to see if their method is good no matter the backbone. And as you can see here, it goes well in many different configurations. So if you use RES 50, RES 101, and with different input image sizes as well. If you use EfficientNet and Cascade as well. So every time with copy paste, you have this improvement in average precision, both for box and mask. They also show how the copy paste method improves or is additive to large-scale jittering and the mix-up method that I explained before. So here you can see that you take the standard scale jittering, the yellow line, and then adding mix-up, and then adding the copy-paste, you get better results. Same thing for the large-scale jittering. Another test they perform is regarding self-training. So self-training, just a recap, is a method where you have a network that is trained on the standard dataset, which is labeled. And let's say this one here. So we have the objects and you have the label. So once it's trained, you have this other data set here with objects in it, but not labeled. And what you do is you take the network that was trained with this and you run it in this one. So it will generate a bunch of labels, which we call here pseudo labels, and you use those labels to train again this network. So it will be trained on the labels it generated itself. This is a funny method, but it works surprisingly well. So if you see here the numbers, this is the result. So if you get the given network with it will give you, let's say those scores here. If you do self-training, you get an improvement. If you do copy-paste, it also gets an improvement, but if you do both together, you get even better results. And here they show that the copy-paste method can be added not only on the original dataset, let's say here the COCO, which has the ground truth information. You can also do the copy-paste on a pseudo data. So if you do on each one individually, you get those improvements, but if you do in the two, you get even better results. And here they show how the method performs well, again, with different state-of-the-art models. So before they were more on different backbones, here they show different state-of-the-art models on COCO, and as you can see, with their model called the Cascade Efficient V7, with copy-paste you get an improvement, and self-training and copy-paste you get even more points on the average precision, both on validation for mask and test for mask and instance. They also showed that this method of copy-paste can help on transfer learning tasks. So let's say you have the network trained on COCO, and then you test it on the Pascal VOC test set. If you go with the model RefineNet or Sniper, you get this average precision 50. But if you use Cascade, EfficientNet, you get a little bit more. So they take the best one and they add the copy-paste idea on top, and then they get better average precision. Here what they do is to take Pascal VOC 2012 and use it on the validation set. So they take one of the methods that give a mean IOU. Actually, it's not the best. Here I'm curious to know why they use this one, not, let's say, the efficient L2, which is one of the highest MYU. And when they use the copy-paste pre-training approach on top of this one, they get 2.7. Next on the list are the results on the dataset called LVIS, which is a data set that deals with the long tail distribution problem. So just a quick recap of this, what does it mean? So let's say you have this plot here with the amount of samples for each class. So let's say you have one class that have 10k images, but then you have like many other classes with 1, 2, 3 samples. Let's say this is dog again, this may be whale, this may be like this super rare monkey. So you know it's a really hard problem to deal with because you have this imbalance and also few samples of many categories. So of course data augmentation help, and they show it here on this table where they take many state-of-the-art models that were specifically designed for Elvis or trained on Elvis, and every time they add a copy paste they get improvements. So for ResNet 50, ResNet 101, EfficientNet as well, and also different image sizes. They also show how the method can also work for a single stage or two-stage training of Elvis. This is a technique really common for this kind of data sets with long tail distribution. So basically the idea is in the first stage you train the network as usual. So basically you use the standard training techniques, and on the second stage use this class balance loss, which basically gives more weight to the classes that are less represented. So this is one aspect of the table. The other one is this RFS, which is another technique for this kind of problem, and this stands for the repeat factor sampling. Basically, in simpler words, it means take the smaller classes and make them more common on the dataset loader. So the network is gonna see more of those less represented classes. So with all that in mind, what you get is improvement when you use RFS. You get even better results with copy paste, and again, in some cases, best results with copy paste and RFS. And close one for the ones that are not the best. The two-stage is similar, so they get, and actually it's similar setup, but the better results are achieved with copy-paste only. So it's not a good idea to use RFS and copy-paste. And that's it for this paper. I hope you enjoyed it. I really liked reading it. It's really thorough on the evaluation of its usefulness on many scenarios. Also, if you are a user of TensorFlow, you can have a direct implementation on the official GitHub of TensorFlow, so check it out. Thanks a lot, and see you next time.